Hello everyone. So in this session, we will be looking at finding limits graphically and numerically. We have already done some of these problems in our previous session. In this session, we are going to look at a rigorous definition of the limit. So let me just recap things we have done in the previous session. So in the previous lecture, we talked about the tangent line problem. We looked at the informal definition of limits, and we studied some examples and a little theory about numerical and graphical approach of limits. In this lecture, we're going to be learning about limits using the rigorous definition, which is basically the epsilon-delta definition. Before I start with this rigorous definition of epsilon-delta, I'm going to do a little recap of the things we have done. Now, remember the classical calculus problem is called, one of the classical, calculus problems is the tangent line problem. What this tangent line problem says is, if you're given a function y equals fx and a point P on its graph, then we are asked to find what is the equation of the tangent line to the graph of this function at a point P. Now remember, if it was a straight line, we can easily find the slope or the equation of this straight line. But if this function is a little curve, then how do we find the equation of the tangent line to the graph of this curve at any point P? What we know is that for cases which are not vertical tangent lines, the problem of finding this equation of tangent line is equivalent to finding the slope of the tangent line at P. So in my previous lecture, I have talked about why do we look at slope, not the equation. If you recall that in the equation of a line, we need a point and a slope, as we are already given the point P here. So we just need to find the slope of the tangent line, and we can easily get this equation of the tangent line. So to find the equation, finding this equation of the tangent line, what do we normally do on this curve? We basically need a point. We need as a point, another point apart from P. We need a point and a slope. So to find the slope, we need another point Q. And then we draw a secant line through the point Q and P. And then what we do is we apply this little approach, which is that we look at various point Q's on the tangent line, on the graph of the function fy equals fx, and we look at the slopes of all these various secant lines. What we notice is, as the secant lines are depending upon where these points Q are on the curve y equals fx, the slopes of the tangent lines, they start to come closer to the slope of the tangent line when these points Q are closer to the point P. So what we say in mathematics is that the slope of the tangent line to the graph of this function is the limit of the slope of the secant lines. Now if you want to look at what is this limit, we have talked about that in the previous lecture. You can go and have a look at that video and the lecture notes. So I'm just going to do a simple example on numerical and graphical and then go to the rigorous definition. So remember in the example last time we said let's have a function fx, x cubed minus 1 over x minus 1. Clearly this function is not defined at x equal to 1. So the calculus says what is actually happening at the point 1 where the function is undefined. There's something really going on. We would like to study that. And that's where calculus comes in place. So what we do is we take some points which are very close to 1, both from the left-hand side and the right-hand side, and then we look at the function values. What we notice over here is as x values are coming closer to 1 from the left or the right, the function values is approaching 3 both from the right and the left. Now, if you look at it from a graphical point of view, which is the next slide, you notice is that this point at x equal to 1, the function is undefined, there is a hole. That's how we define it here. Now notice graphically as we are approaching x from the right hand side and the left hand side, the function is also approaching 3 from the left and the right. So the informal definition which we have looked earlier is defined as this. It says, if a function f(x) becomes arbitrarily close to a single number L, as x approaches c from either side, the limit of this function f(x) as x approaches c is L. In notation form, it is written as this. The limit of f(x) as x approaches c is L. Now, for example, if I take the limit of x approaches 3 of this function 2x plus 1, so clearly if you notice, this is an equation of a line. And if we draw the graph of this line, we would notice that when we draw 2x plus 1, so clearly it's going to be a line like this. And at 1, the value of this function is 7. Okay, now, since the limit value is 7, the question now comes and says, how close do we make this 2x plus 1 to 7? And in order to do that, we have to see how close x is coming to 3. Sorry, it was 3. Sorry, here it's not. Yeah, it's not 1, it's 3. So as x is coming closer to 3, the value of the function at when it is 3 is 7. 0, it was 1. I'm sorry. Yeah, it was my mistake. Sorry for that. So the question is, suppose now we say how close do we want this function 2x plus 1 to be 7? Suppose we say we want to be within 0.01 of 7, like 1/100th of this, closer to 7. So then the next question is how close that x has to be into 3 in order to guarantee this. This is what is going to lead to the formal definition of the limit, and we also call it the epsilon-delta definition of the limit. Now, before I do the formal definition, I'm going to start with an example to explain it to you. So, the limit as we found of 2x plus 1, this function as x approaches 3 is 7. We have that over here. Now, we would like to have this function 2x plus 1 to be within, say, 1/100th 0.01 of 7. So the things we're saying is how close x must be to 3. So what we do is we write 2x plus 7 and we add. Now remember, it's like 1/100th. That means it can be, it can be a little bit more than 7 or less than 7. So that's we're saying this function is less than 7.01 or greater than 6.99. So this is basically 7 plus 0.01 and this is 7 minus 0.01. Okay, so when we do the math over here, it's 6.99 strictly less than 2x plus 1, strictly less than 7.01. And now the thing is we've got to find x because we want to know how close x must be, which simply says solve this inequality for x. Get rid of the get rid of the terms which are next to x, so that you basically remove positive 1 and then divide by 2. So when you subtract minus 1 from both the sides, we get 5.99 less than 2x less than 6.01 divided by 2. So we get that x lies between 3.005 and greater than 2.995. So thus, which says that x must be within 0.005 of 3. Now that was the very simple way of doing it. So we're going to apply a little bit more mathematics here. Now we can solve the same problem using absolute values. Remember, absolute value gives us the distance, and distance can be, if you're looking at the distance, say a distance from 7, it can be ahead of 7 or less than 7. So distance is what we're going to use in terms of absolute values. So if you will have two numbers, the distance between of these two numbers is given by a minus b. So remember, we have this function. This is given 2x plus 1, and at 3, we're looking at this. So you're looking at this distance. Like, what is this distance? Below and less. So so this point is 2x plus 1 minus 7, absolute value is less than 0.01. And then again, we're just going to solve for x. So when you just now do simple calculations, 2x minus 6 less than 0.01, take the 2 common out, and you have 2x minus 3 strictly less than 0.01. Now, absolute value properties. So if you have a times b, you can written as absolute a, absolute b. That's what we are doing. Absolute 2, absolute of x minus 3, strictly less than 0.01. Now, absolute value of 2, remember, is a 2, and then you solve, and what you're getting is x minus 3 strictly less than 0.01 by 2, or x minus 3 is strictly less than 0.005. That means x must be within 0.005 of 3. So two different ways of applying the formal definition. So now guys, I am going to give you the formal definition of a limit. So let f be a function which is defined on an open interval containing c except possibly at c. And let L be a real number. The statement limit of fx as x approaches c is L means that for each epsilon greater than 0, there exists a delta greater than 0 such that if 0 strictly less than the absolute value of x minus c is strictly less than delta, then the absolute value of fx minus capital L is less than epsilon. Now these epsilons and deltas are very, very small numbers. So what I'm going to do is, I'm not going to go more further into this formal definition. I'm going to use this to actually show you, with the help of example, how to find the deltas for a given epsilon. And that's what, guys, we're going to focus only on. So, okay, so let's start with an example. We will use the epsilon-delta definition to find the limit for the following. We're going to find the limit of 2x plus 3 as x approaches 1. So what I've done is I have written down the steps you need to find the delta given epsilon. So the first thing is you find L. Now, what normally happens is whenever you have a nice little function which is a polynomial, you simply go ahead and substitute the value where x is going into the function. That's basically called direct substitution. Or if you have a rational function where there is no problem in the denominator, you just go ahead, take the value where x is going, substitute it in the function. Remember, this is, guys, the function fx. So the limit, so what we do is we take 1, substitute in place of x, we get 2 times 1 plus 3, which is a 5. So the limit of this value is a 5. Now we just have to find the delta based on the epsilon. So let's look at step 2. In step 2, what we have to do is for each epsilon greater, now this epsilon is an arbitrary, it's a variable, very, very, very small and very, very positive. There exists a delta. So you say for each epsilon strictly greater than 0, that means this is kind of given. There exists. That means based on epsilon, you will find a delta such that when the difference between the absolute value of fx, remember this is fx, minus L is strictly less than epsilon, looking at the absolute value here, whenever 0 strictly less than x minus, now remember this is your c, less than delta. So what we're trying to do is, we are trying to find an appropriate delta which will establish a connection between this expression, 2x plus 3 minus 5 and x minus 1. So what we do is, we write down fx minus L, we start with the difference between fx and L, and then go and continue till we see the x minus 1. So we just substitute like fx minus L, that's 2x plus 3 minus 5. It's kind of a typo, guys. Just remove this. Okay, so Solving this, 2x plus 3 minus 5, 2x minus 2, take the 2 common out. We're doing everything inside the absolute value. And then normally the way we did in the previous one, take this is 2 times x minus 1. So you can write this as absolute value of 2, absolute value of x minus 1, and absolute value of 2, which is a number, simply a 2, x minus 1. Now, remember, we've already got x minus 1. What are we looking for? 0 less than x minus 1 less than delta. In other words, we want to have the coefficient of the absolute value of x minus 1 to be a 1. We have a 2, and that is the clue. The delta basically is going to be epsilon divided by the coefficient in front of x minus 1. That's it. So for a given epsilon greater than 0, we can choose delta to be epsilon divided by 2. This is where it comes down, guys. That's where you put. So this choice will work, as you will see in the next slide, because when you're looking at 0, strictly less than x minus 1 delta equals epsilon by 2. So when we go back over here, we have fx minus L, once again it's a little typo, is less than 2x minus plus 3 minus 5, which is 2x minus 2, 2 less than x minus 1. So when this is here, this delta, remember this 2x minus 1 is 2, this is less than, because that's what's given, x minus 1 is less than delta, 2 times delta, and this delta is epsilon by 2 and less than epsilon. That's why you have to choose your delta very carefully, and the trick is lying here. That's the trick. You'll always have an epsilon in the numerator divided by what is the coefficient of in front of x minus 1. Keep that in mind. And the absolute value of x minus 1, sorry. Okay, so I'm going to do another example, which will give you an idea how to do these problems. So use the epsilon minus delta definition to find the limit for the following. The limit as x approaches minus 2 for the function 4x plus 5. Step 1, you find L. What basically, if you notice this function 4x plus 5, you simply go ahead and substitute wherever the x is going. So remember, this is your C. Plug it over here wherever the x is in the function. So 4 minus 2 plus 5 minus 8 plus 5 minus 3. So the L value, the limit for this function is minus 3. Now we have to find the delta for this given epsilon. The same thing we did in the previous example, we're just going to follow it. So what we have to do is you have to show for each epsilon there exists a delta such that 4x plus 5 minus of minus 3. Remember, it's a minus is this. This is important. This is a very key important. It's fx minus L. My L is a minus 3. Whenever 0x minus, now remember this is C, less than delta. So what happens? We're trying to find the delta which will establish a connection between this fx minus L and x minus C. So when you put fx minus L, which is 4x plus 5 minus of minus 3, which makes it positive 3. So you get 4x plus 5 plus 3, which is 4x plus 8. And then you can take the 4 out, x plus 2. It's all happening inside the absolute value. So once again, we do the same thing. Take absolute value of 4, absolute value of x plus 2. So it's 4 times x, no, x plus 2 is the same as x minus of minus 2 here. Now remember, oh, there's a typo here. This is epsilon by 4. So whatever is in front of x minus of minus 2, that pops up over here. And that's basically your delta value. Okay, so once again, we go and do the whole process. So we have to find this epsilon. We say 0 less than x minus 1 less than delta equals epsilon by 4, or fx minus L. And basically the whole thing, 4x plus 2. Remember this x plus 2, guys. Oh, x minus plus 2. Again, it's a typo. So x plus 2 less than delta. So this is going to be strictly less than 4 times, let's say less than symbol, because of x plus 2 times delta. Now remember, delta we chose to be epsilon by 4. So 4 times epsilon by 4. So fx minus alpha is strictly less than epsilon. And that's what is needed for you guys for the rigorous definition of a limit. And as usual, I give you 2 practice problems. So there are 3 problems I would like you to practice. So limit of this function 5x minus 7, x approaches 2, or 7x plus 8, x approaches minus 1, and x approaches 3 of 3/4 x plus 1. Okay, thank you guys.